I wanted to at least get this far. There's something called Hooke's law. This is like a classic example. I don't know that, I don't know why they make such a big deal about it. Maybe it's just a simple example, but Hooke's law states that the force required to maintain a spring stretched X units beyond its natural length is given by the following formula. So the formula is f of x is equal to k times x. And this k is called spring constant. So I guess if you just leave a spring alone, it has a natural length. So let's say this is the natural length. And then let's say that you stretched it out. If you stretched it out, maybe it looks like this. So what you could see is that we've stretched it beyond its natural length by X units. And when you stretch out a spring and you hold it there, that requires force. So some of you guys are into working out. That's like isometrics, right? Isometric workout, like you take a spring, you stretch it out and you hold it. You're exerting a force to hold it out there. And if you've ever done any sort of stuff like that, the further you stretch it out, the more force it takes to hold it out there. So if we were to look at an example, they tell me that a force of 50 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. Okay, so what can I deduce from that? Well, I know that if I have the force, we know that force is equal to k times x, right? And they tell me that 50 newtons is required to stretch it 15 minus 10, which is 5 centimeters beyond its length. So, so I hope you can see that this is going to be 50 is equal to k times 5. Now, we're used to working in, these units are in centimeters. So this would be 5 centimeters. But as I mentioned to you guys earlier, usually we work with meters when we're in the metric system. So my goal is to solve for k, but I think I'd rather write 50 is equal to k times 0.05 meters. Now it'll be in meters. So there's 100 centimeters in a meter. So we can convert to meters, right? And then this tells me that my k is equal to not just 10, but 1,000. Okay. So my force, now I have a equation using Hooke's law to represent the force of the spring. And that's going to be 1,000 x. Great. So they say how much work is done in stretching the spring from 15 centimeters to 18 centimeters. So I know that I want to set up my work equation. My work equation is going to be equal to the integral. It's going to be f of x dx. I'm going to write in certain parts here. My f of x is going to be 1,000x, and my going to have a dx here. I guess my question for you is, what do you guys think the limit of integration should be over here? Well, remember, x represents the distance beyond the natural length. So the natural length was 10, right? If I'm starting at 15, you might think I want to write a 5 here. I think that would be a good thing to think, except because 15 centimeters is 5 centimeters past 10. But I kind of want to work in meters. So instead of writing 5 centimeters, I'm going to write 0.05. And that's going to represent the distance in meters. I can do the same thing with the 18 centimeters. 18 centimeters is 8 centimeters beyond the natural length. So instead of writing 8 centimeters, I'm going to write 0.08 meters. Then I can evaluate this integral. The antiderivative of 1000 x is 1000 x squared over 2. That's equal to, evaluated from 0.05 to 0.08. That's equal to 500 x squared, evaluated from 0.05 to 0.08. And that's going to be equal to 500 times 0.08 squared minus 0.05 squared. So I can pop that into my calculator. I got 500 parentheses 0.08 x squared minus 0.05 x squared, close parentheses, enter. I get 1.95 Newton meters. And that's going to be my answer. All right. Is there any questions about this, my friends?